Today we are going to be discussing energy and springs. Springs is something that we did not cover before, but now is as good a time as any. We have to backtrack a little bit to understand springs. We need to first talk about springs themselves before we can talk about spring energy. Springs are governed by a principle called Hooke's law. Hooke's law. It says that the force from a spring is equal to negative k, whatever that is, times x, which is some distance. That negative sign, that's actually very important, so that's something to not forget. But this means that you have some constant here. That x represents how much the spring has been compressed or stretched out. You can compress a spring, if you have just a spring sitting there with nothing, no forces acting on it, it's just going to sit there at some length. It's like taking a slinky or something and just laying it down on the floor. Well, it's just going to be a certain length. But you can try to stretch it. And x is how much you have stretched it or compressed it. K is the spring constant. The spring constant measures how rigid the spring is. A spring that is very difficult to compress or stretch is going to have a very large K value, very large spring constant. So K is just a measurement of how difficult it is to stretch or compress a spring, and X is how much you have stretched or compressed the spring. And force is the force that spring is pushing back. If you compress a spring, it's going to push back on you. If you try to stretch a spring, it's going to try to contract back down. That's what the negative sign tells you. If you take a spring and you try to stretch it like this, it's going to want to pull back like this. So if you give it a change in length this way, you add length that way, it's going to want to contract. Likewise, if you try to smush a spring, then it's going to want to expand. So if you change its length this way, it's going to want to go like that. That negative sign takes care of that. Oh, question. What is the spring constant? It's how difficult it is to stretch or compress, and it's denoted with K. K is the way that we denote spring constant, but it's how difficult it is to stretch or compress. Actually, I did want to say more about that. The units for spring constant are newtons per meter. So you might have one spring constant that takes, say, 10 newtons to stretch it out by 1 meter. If it takes 10 newtons to stretch it by 1 meter, if it takes 10 newtons of you pulling on it to stretch it by 1 meter, then the spring constant is 10 newtons per meter. You might have, that's a very weak spring, by the way. You might have a spring that is much more rigid. And a much more rigid spring, it might take 10,000 newtons for it to stretch 1 meter. You can imagine taking one of those hand exercise things. You've seen them in stores, Walmart, I don't know, where it's a exercise tool that you use to strengthen your hands, and you can have different versions of that. And there's versions of it that are very easy to smush, and there are versions that are much more difficult to smush. That means that they have different spring constants. The springs inside those exercise thingamajigs have different spring constants. A sturdier spring will have a higher spring constant than a very weak kind of spring. Like the spring that you have in a mechanical pencil, we've all taken apart mechanical pencils and pens and whatnot and taken the spring out of them. Those are very weak springs. The shocks on your car are going to be very much more difficult springs to compress. And so a spring in your pencil or pen is going to have a very low spring constant, while the shocks on your car, which are springs mostly, those are going to have a much larger spring constant. That does mean that even something like the shocks on your car, if you had just a spring from one of your from the shocks on your car, you can actually compress it a tiny, tiny, tiny amount, just with your own force. You should be able to compress it by like a millimeter or something like that. But by the time you've compressed it by 1 millimeter, you take the 1 millimeter, convert it to meters, multiply it by the spring constant. Remember, the force of a spring is negative k times x. So if you can compress something by 1 millimeter, multiply that by the spring constant, 1,000 newtons per meter or whatever, and you get how much force you have applied to it. And that's also true with a very small spring. You can take a small spring and smush it very easily. And so you say, okay, well, you're actually still just smushing it like 2 centimeters or something like that. Convert that to meters, multiply it by the spring constant, and that's the magnitude of how much force the spring is pushing back on you with. Does that make sense? Are there any questions about that? It does vary, yes. It varies based on the spring. Different springs have different spring constants. And for the sake of tests and whatnot, I would either give you the spring constant or I would ask for the spring constant or something like that in any problem like that. Or I'd give you enough information to calculate it on your own. Let's do an example with spring constants. A 3.5 kilogram weight hangs off of a spring. Imagine taking a spring and attaching it to the ceiling. And you just let it dangle there, I guess, but then you come along and you attach a 3.5 kilogram weight to the end of it, a 3.5 kilogram mass with some amount of weight. The spring then stretches 18 centimeters while holding the weight. We can use this to calculate the spring constant. We can start out by drawing our situation. I've attached a spring to the ceiling. And then I say, okay, I've come along and I've attached my 3.5 kilogram weight to it. And it stretches by 18 centimeters. And we need to find K. It's always a good idea to start off with drawing a free body diagram for a situation like this. We know that this weight, this mass, has 2 forces acting on it. One is the force of gravity pulling down, and the other one is the force of of the spring pulling up, force of the spring pulling up. You might be tempted to call it the normal force, and that's not really wrong. It's just less precise. It would be better to call it the force of the spring. Normal forces are for usually when one thing is trying to pass through another thing, but okay, it's effectively the same thing. It's just more precise to call it the spring force rather than the normal force. Well, it certainly doesn't look like the mass is oscillating on this, and so the acceleration of this can be presumed to be 0. If that's 0, then this force of the spring has to cancel out with the force of gravity there. So that tells us about the relative magnitudes of these two. They should be equal. We can take that piece of information, saying that they are equal forces. One is going up, one is going down. And we know from Newton's third law that the spring, if the spring wants to contract with a certain amount of force, and according to Hooke's law, according to everything we know about springs, the spring wants to contract with a certain amount of force. That's going to be applied to this object. So we can just say that that vertical force there is the spring force based on Newton's third law. We can then plug in what we know, that the force of a spring is negative kx, and that the force of gravity is mg. We know that the object has gone down by 18 centimeters. It's stretched downward by 18 centimeters, and so we get a negative 18 centimeters in there, which ends up becoming negative, I'll write it down, negative 0.18 meters, of course. We need to get all this into meters because the units of K, as I showed you on one of those slides, but I didn't actually mention it, the units of K is newtons per meter. Newtons per meter. If something takes 100 newtons to get stretched 1 meter, then the spring constant is 100 newtons per meter. If it takes 10 newtons to be stretched 2 meters, then it would be 10 newtons per 2 meters, or 10 over 2 newton meters, or 5 newton meters. So we need to get everything into meters to get good units. We're searching for K. We plug in the 0.18, and the negative sign goes away. We had a negative sign out front, but because of that negative sign, it goes away. And that's equal to 3.5 times 9.8. Now, one of the easiest places to get messed up in looking at springs is you forget to deal with the negative sign. That negative sign means that if you're trying to compress something, it wants to expand. If you're trying to compress a spring, it wants to expand. If you're trying to stretch a spring, it wants to contract. We know that that's how springs work because, you know, we've all seen a spring before in our lives. We know that if we start compressing a spring, it does not feel a force that makes it want to compress itself more. If that was true, if springs started compressing more, if they had if that negative sign was gone and compressing a spring made it want to compress even more, then you'd take a spring, you'd compress it a little bit, and then it'd want to compress more. And so it'd compress more, and it would want to compress more, and it'd compress more, and it would shrink down into a black hole or something like that. And if you tried to stretch a spring, it would start expanding out, and then it would want to expand out more, and it would expand out more, and it would suddenly be stretching out at the speed of light. And we know that that does not happen in our universe. Therefore, the negative sign is very important. However, if we forget the negative sign, the only thing that's going to change is that we would get a negative value for the spring constant. And if spring constants are always positive, we're always just going to have a positive spring constant. So if you ever get a negative spring constant, that just means that you dropped a negative somewhere and you probably shouldn't have. And so you can just make it positive again. Question, why did we get negative 18 centimeters? It's because the spring was stretched downward by 18 centimeters. If you go down by 18 centimeters, then that's a negative because, you know, y is, if you go up, y is more positive. If you go down, y is more negative. So stretching down, you get a negative sign. We can then solve for K, and it's just one equation and one unknown. So we get 191 newtons per meter. Newtons per meter. The one somewhat slightly important point with all that is that the negative sign, it doesn't really matter as long as you're comfortable with saying, oh, well, if I get a negative for K, I know that that's wrong and I just need to make it positive. That negative sign isn't going to ruin anything if you forget about it because the K is always positive. So if you get a negative K, then you know that you just did something incorrect with a negative sign and you can just change it back and that's fine. Now that we've done that pretty simple problem, we can move on to spring potential energy or potential spring energy. We've already talked about gravitational potential energy being UG. Now we have US. That is potential spring energy. U, for whatever reason, is potential. And so now we have potential spring energy. You can think of this as, if you take a spring and you compress it, well, then it has the potential to go boink like that and shoot off somewhere. You take one of the springs out of your mechanical pencils, which I did this plenty in high school, and I'd take that spring when I was bored because the professor or the teacher was being super boring, and I'd press on the spring, and then suddenly I'd lose control and it'd fly around the room. I ruined many mechanical pencils just by taking out their springs and playing with them. But you compress it down like that, and then it has the potential to shoot off somewhere after you accidentally let it go. That is spring potential energy. It also works if you stretch a spring, it really wants to snap back, and it has the potential to snap back and somewhat violently snap back if it's a sturdy enough spring. That's spring potential energy. If you take one of the little mechanical pencil springs and you compress it, you have given that spring energy that it can then release somehow. If you stretch a spring, you've given it energy that it can then release somehow by stretching back. And we call that spring potential energy because we have given that object some energy that gives it a potential to do something. Just like taking an object and lifting it up, that gives it the potential to, hit something like that. Lifting it up a little bit, not a whole lot of potential to do much. Lifting it up more, it's got more potential to cause some violence there, some hit like that. So same sort of principle as gravitational potential energy, but just for springs instead. The equation for spring potential energy, US, is equal to 1/2 times K times X squared. Here's another place where the negative sign isn't going to matter. If you stretch a spring by 8 centimeters or compress a spring by 8 centimeters, well, if you stretch it, that's probably going to get you one sign, and if you compress it, it'll get you the other sign. And that then gets squared though. So if one of them is negative, then it gets squared and it doesn't matter anymore. Spring potential energy is always positive. So stretching or compressing by 8 centimeters, 16 centimeters, 99 centimeters, whatever it is, you stretch it or compress it, positive or negative, it gets squared, and that positive or negative just becomes positive. So that X is how much you've stretched or compressed the spring. K is again the spring constant, same thing, newtons per meter, and then you've got the 1/2. This looks really suspiciously similar to kinetic energy, 1/2 mv squared. And you have the same units. Energy is energy, so this is still going to be measured in joules, just like all other kinds of energy. But instead of 1/2 mv squared for kinetic, it's 1/2 kx squared for spring potential. I've got a couple example problems with this. A spring in a physics lab launcher has a spring constant of 12 newtons per meter. It is compressed by 0.09 meters, or 9 centimeters, and used to fire a 20-gram ball. How fast is the ball going at the moment of launch? Old toys from the 80s and 90s had little spring-loaded launchers in them, but I guess they caused too many injuries or something, and nobody builds toys with little spring-loaded launchers in them. But these were much more common back a while ago, I guess. But you've got a spring, you compress it, you use it to fire a little object of some sort, and we need to find how fast the ball is going at the moment of launch. We need to find V at the moment of launch. I have recreated the problem here. We've got a spring, and we've got the ball there. We need to find V final. We're told that we have compressed the spring by 0.09 meters originally, and the mass of the ball is 20 grams, and the spring constant is 12 newtons per meter. We start with the same equation as ever. Delta E is equal to work other. Now, we did not go over this specifically, but remember how we had work due to gravity over here. We used to have work due to gravity over on this side, and then we found the relationship between the work due to gravity and the gravitational potential energy. And I said, we're going to ignore work due to gravity and just fold that principle in with delta E. We're doing that again. There is work done by that spring. Obviously, that spring is exerting a force over a distance, and work is force times distance times cosine of theta. So there is work due to that spring. However, by implementing the spring potential energy, we don't need to deal with the work due to the spring. We can just plug that right into the energy. So we can measure 3 different kinds of energy now. We've got 3 different kinds of energy to think about. We've got kinetic energy, we've got gravitational potential energy, and now we've got spring energy. That all can go on this side. On this side, the one thing that we've actually done much with is friction. We have applied friction to this work other. There are other things that can do work, like physically pushing some object that does work to it, but mostly it's going to be friction over here. We know that there's no actual friction going on in here, or at least friction wasn't specified, so we can assume that the work other is going to be 0. There's no friction, there's no other person pushing on anything. We're going to fold the spring potential energy in on the delta E side, and so delta E is equal to 0. And energy final is equal to energy initial. Delta E can be broken up into E final minus E initial. Do a little bit of algebra, you get to that. We should note, and I say this here, at the beginning of the problem, all of the energy is stored in that spring. Imagine the beginning of this problem with that ball just resting on the spring, but the spring has been compressed, so all the energy is just spring potential energy. And then we fire it. And the moment after it's fired, all the energy is now the kinetic energy. The ball has not had time to actually go up, hardly at all. So we don't have to deal with changes in gravitational potential or anything like that. We can just say, well, it's now all just kinetic energy right here. It all started off as spring potential, now it's all kinetic. So we say, well, our kinetic energy is 1/2 mv squared. Our spring potential is 1/2 kx squared. You see that a lot of things can cancel out. You can cancel out the 1/2s on both sides. And then if you can do something with the m and the k somewhere, then you just take the square root of both sides and v becomes proportional to x, which I think is kind of neat. Look at it just like this. If you double actually, let's make it a little bit more interesting. Let's triple x. You can think about what happens if you triple the value of x. Well, this side goes up by a factor of 9. If you triple this thing and square it, this side goes up by a factor of 9. If this side goes up by a factor of 9, this side has to go up by a factor of 9. We probably did not increase the mass of anything by a factor of 9, certainly not that projectile. So that means that this thing had to go up by a factor of 9. If that went up by a factor of 9, then v had to go up by a factor of 3. If you tripled x, then you had to triple v, algebraically. It's then very quick to just solve for what the v final is. We know that x is 0.09. We know k is 12 newtons per meter. 1/2 is just a number, and we got rid of it because it's on both sides. Divide both sides by 1/2. The mass is 20 grams. The hardest part there is converting this to kilograms, which it's just going to be 0.02 kilograms. And then you've just got one thing left to solve for, and that's the velocity. And you get 2.2 meters per second. In this case, in this setup, the velocity and the distance that you have scrunched the spring are proportional, but only because if you take the square root, imagine just taking the square root of both sides and canceling out the 1/2. I'll write it down. Let's cancel out the 1/2, so it's just mv squared is equal to kx squared. Take the square root of both sides, and you get v times the square root of m is equal to x times the square root of k. And so if you increase v, you increase x. If you're keeping m and k the same, then doubling v means you have to double x. And multiplying v by 5 means you have to multiply x by 5, because they are equal to each other. This time, we have a spring in a physics lab launcher with a spring constant. I changed it a little bit. I made it 17 newtons per meter, whatever. It's compressed 12 centimeters, 0.12 meters, and the ball now has a mass of 25 kilograms. So I made a little bit of change. Now we're going to say that the ball is launched straight up. And instead of asking the velocity when it leaves the lab launcher device, we're instead going to ask how far up does that ball go? So I've drawn it out here. We've got our launcher device with the spring. These devices are very, very common in physics labs, so you may have seen them before. And it's compressed 12 centimeters or 0.12 meters. The ball has a mass of 25 grams. The spring constant is 17 newtons per meter. And then we launch it and we measure how high up it goes before it stops and crashes back down. And so we start off this kind of problem like we start off any of these problems. The change in energy is equal to the work done by outside forces. Now, there are no outside forces. There's no friction. There's no one pushing on it. And we are including the spring stuff over here in delta E with spring potential. So delta E, final minus initial, is equal to 0, work other. Energy initial is equal to energy final. If you don't have any work being applied to your problem, then energy initial will equal energy final effectively all the time. Well, if you have no other work, then yeah, that is going to be true. Now we have to think, what is our initial energy and what is our final energy? Our initial energy, well, the initial point of the problem is when the ball is in the launcher. That is the initial state of the problem. The final state of the problem is when the ball reaches its maximum height. So initially, all of the energy had to be spring potential energy. And at the end, all the energy had to be gravitational potential energy. Now, when it was here, it had no spring potential, but it did have some kinetic and some gravitational potential. When it was here, just barely out of the launcher, then it was almost entirely kinetic and only a tiny amount of gravitational potential. When it's here, it's very little kinetic and mostly gravitational potential. But when it's here, it is entirely gravitational potential and no kinetic, because this is the point that I'm saying that it gets to its maximum height, and at its maximum height, it has to stop, because if it didn't stop at its maximum height, then it would go higher, and so that wouldn't be the maximum height anymore. So at the maximum height, the velocity was 0, the y velocity was 0, and it has to start coming back down. So here, there's no kinetic, but there's plenty of gravitational potential. So that is my final energy. My initial energy being the spring potential energy. I can mark that down here. My potential spring energy initially is equal to my gravitational potential energy at the end, the final. I can plug in the equations. 1/2 kx squared is equal to mg y final, whatever the final height is. And then I can plug in everything I know, got the spring constant, got the x, I remember to square it. Remember to square it. People mess this up when they forget to square. And that's equal to 25 grams or 0.025 kilograms times the acceleration due to gravity, 9.8, times the final height, y, and I can solve for final height. It's about 1/2 meter. Notice that kinetic energy never actually occurred in here. We never dealt with kinetic energy in there. And that is totally okay. There is definitely kinetic energy in the middle, but nobody cares if there's kinetic energy in the middle because, well, we don't deal with that. We've just got the initial and the final. The best, I guess, example of this that I can think of is if you want to convert your dollars into euros, you can either convert your dollars into euros directly, or you can convert your dollars to Canadian dollars and then your Canadian dollars to euros. And, well, you're still going to end up with the same number of euros as long as you're not being cheated by anyone. And so it doesn't matter that you converted to Canadian dollars in the middle or not. And so any kind of energy that it has in the middle we don't really care. As long as it's not losing energy, as long as you're not being cheated, then it doesn't matter what it's doing in the middle. It only matters what you had at the beginning and what you had at the very end. The important part of this is that we never really needed to deal with the kinetic energy in the middle. We just needed to deal with whatever the energy was at the beginning and the end. Got one more energy problem for today, and it's this. And it looks awful and crazy, but it's actually I hope that you see that it's not nearly as difficult of a problem as it looks like at first. A 7.8 kilogram block starts from rest and slides down a rough incline. This is my version of a rough incline right there. The friction experienced by this block is equal to 15 newtons. That's while it's on the rough incline, it's experiencing a friction equal to 15 newtons. Presumably up the ramp. If it's sliding down the ramp, then the friction it's experiencing is up the ramp. The block starts off 3 meters above the ground, so its vertical height is 3 meters above the ground, and it slides 5 meters down this rough ramp. So this little bit right there is 3 meters, and the distance down the ramp is 5 meters. And then there's a frictionless plane that's 4 meters long. The block then hits a spring, compressing it. The spring constant is 9,100 newtons per meter. How much is the spring compressed? I have recreated the setup here. Got the block that slides 5 meters down this rough incline. It starts off 3 meters above the ground. And then this part there is going to be 4 meters. The force of friction going up the ramp is 15 newtons. The mass of the block was 7.8 kilograms. The spring constant there is 9,100 newtons per meter. And we need to find how much the spring is compressed. And so we start, like we start all these, we say that delta E is equal to the work from any other force. And this time we do have another force that we haven't included in delta E, and that's the force of friction. We finally have a work to put in here again, force of friction. So the change in energy is equal to the work due to friction, the work due to friction. And so we can say that the delta E is equal to, well, the equation for work is force times distance times cosine of theta, but we know what kind of force it is. It's the force of friction, so I'm going to indicate that there, that it's the force of friction. Delta E is just E final minus E initial, and that's equal to the force of friction times D times the cosine of theta. Energy final. We have to decide what to plug in for energy final. Well, the final state of this problem is when the block has come in there and compressed the spring a little bit. Now, if we choose there to be H equals 0 or Y equals 0, however you want to do it, the ground is 0 meters. Then there's no potential energy. There's no gravitational potential energy for that block or that spring at the end of the problem. There's no kinetic energy at the end of the problem because the block has compressed the spring by the maximum amount that it will. There's only spring energy at the end of the problem. At the beginning of the problem, the spring is not compressed, and so there's no spring energy. At the beginning of the problem, the block is not moving. There's no kinetic. At the beginning of the problem, it is all the way up here at the top of that ramp, 3 meters above the ground. That means that there will be gravitational potential at the beginning. And so my final energy was the spring energy over there. My initial energy was the gravitational potential energy up there. And that's equal to the force of friction, which I gave you as 15, times the distance down which it moves. Well, the distance that it actually moves is 5 meters. That's why I gave you both of those distances. It's 3 meters above the ground, and so that's what the gravitational potential energy cares about. But it slides 5 meters down the rough surface. And so that is what the energy lost due to friction cares about. That's the displacement that it undergoes. The force of friction is up the ramp, and we're sliding down the ramp. And so the angle between up the ramp and down the ramp is 180, and the cosine of 180 is -1. And so we've got a -1 there. Remember, friction removes energy. And so if you've got friction, you should expect a negative amount of work. We can replace the spring force, the spring potential, with the 1/2 kx squared. So spring potential energy, 1/2 kx squared. Gravitational potential energy, mgy. This is the final compression of the spring. That's the initial height of the block. It's equal to -75 joules. You plug in everything that you know. 1/2, k is 9100. X is what we're looking for. M is 7.8. G is 9.8. Y is 3. All equal -75. And you solve for X and you get 0.184 meters. So that huge looking problem actually took this much math. That's not too bad. For a problem that took that many words to explain, this is all the math. We don't care that it was going at a certain speed there. It was definitely going at a certain speed there along this frictionless part. Nobody cares because it doesn't matter. It's like converting your dollars to Canadian dollars to euros. Nobody cares that you go through the intermediate step. You should still have the same money at the beginning or the end unless you're being cheated by friction, and friction is removing energy. Then you do have to deal with the energy removed due to friction, but still you can just say, well, what's my energy at the end when I've compressed the spring compared to my energy at the beginning when I'm all the way up there? Well, the difference between them should equal the energy that I've lost due to friction, -75 joules. And then you just solve and you get whatever you get.